As it mentioned before, based on Snell's law, when you have two materials with two refractive indices, at the interface between the two materials, for example, like here, in this side, we have air, in this side, we have glass, which has a different refractive index, it's around 1.5. And here again, we have refractive index of glass, and here we have air. At this interference, when the light is passing and it is not perpendicular to the normal vector, the light is going to get bended. Like here, you can see the beam is parallel to the optical axis, is parallel to the optical axis of the lens, and is bended at this point. And because the refractive index of the glass is higher than the refractive index of the lens, this angle compared to this angle is smaller. So the light is get closer to the normal vector. And we have the same situation here, but the light is get further from the perpendicular vector to the interference. And the point is that at each point, this normal vector is different. For example, here the normal vector is in this direction. Here the normal vector is in this direction. If you go a little bit higher, the normal vector is a different direction because all the if we consider this surface as a spherical surface, all the normal vectors goes to one point, which is the center of that sphere. So if we solve Snell's law for this lens, then for all the rays that is coming from infinity or that are parallel to the optical axis of the lens, for ideal lens, all of them get focused to one point. And that point, we call it the focal points of the lens or the focus point of the lens. So right now, we need to do some approximation because our lens is not, this equation is correct only for paraxial approximation, which means that when your rays is pretty close to the optical axis of the lens or the theta is very small. When the theta is very small, we can approximate sine of theta with theta. It should be around 6 degrees. Then we can use that approximation. Tangent of theta is equal to theta. Cosine of theta is equal to 1. So the limit of theta goes to 0, then we can use that kind of approximation. And when we use that kind of approximation, we can say we are in paraxial approximation regime. And for most of optical systems, we use this kind of approximation. And we're gonna talk about different aberrations in next lessons. But for now, let's just focus on paraxial approximation. So based on paraxial approximation and using the Snell law and putting equations together that I'm not going to talk about it right now, we can get to this equation that we call it image formation equation. That on this side we have 1 over f, which is a number associated with this lens, and we call it the focal length of the lens. This f is the focal length of this lens, equal to 1 over SO, which is the position of the object from the center of the lens, and SI, which is the position of the image from the center of the lens. So when we put these two numbers, we can get to the focal length. But now let's delve into the concept of image formation. What does it mean? We usually put an arrow and then we put a lot of beams and then all of them get focused on one point. So in this image, you can see I have a arrow, but this arrow is a little bit smaller. So it means that we have some kind of magnification, but magnification is smaller than 1. So all the beams that are originating from the tip of this beam, you can have different kind of beam. All of them get converged into one point. And then for another pixel, or it's better to say another part of your image, if we consider it as a one point, then it's gonna converge to another point. So a lens system is a one-to-one system that image the whole object into even a smaller or bigger surface. So if we put a surface here, then we can see all the point source that you have here imaged on that surface. So in this slide, we can see this concept more clear. So let's say we have an object that is like this, and if we draw the lines, use the paraxial approximation and Snell's law, we can get to this image. So right now we have a magnification which is smaller than 1, but that's the concept of imaging. So instead of that, you can put an arrow, and then you can put another arrow here. Instead of this one, you can put the arrow here and then another arrow. Actually, this is not completely correct, but I wanted to show you the concept. So for each point of your object, it's gonna map into another point that we call it image. So that's a concept of image formation. But we should be very careful, because all I explained, that was, for example, for SI is a distance. It can be positive. I mean, the distance is a positive number, but depends on the direction or the side of the lens. We should manually put the value, negative or positive sign for those values. For example, if your object is on the left hand side, everything that is on the left hand side we put negative sign. Anything that is on the right hand side we put positive sign. Anything that is under the optical axis we put negative sign, and anything that is uh, higher than the optical axis we put positive sign. And it is true for everything, even the radii of curvature. Then in the next lessons I'm going to talk about the radii of curvatures. That's the lens sign convention, which is pretty simple: negative, negative, positive, positive.